For the second half of the video here to finish out chapter 10, we're finishing up vapor pressure and how it reacts to temperature. Now, as we know, as temperature increases, vapor pressure increases, and it's really quite obvious um, if you think about hot water is producing steam. So as temperature has increased, I can see evidence of that's in that steam that the vapor pressure has been increased. So obviously the opposite is true, that when I decrease temperature, vapor pressure decreases. Now the book goes into this explanation about how the graph of pressure versus temperature is nonlinear. So it's going to look something like this, and you can see pictures of this. It's got a curved line, and it's not very useful unless we know calculus, and we don't need to know calculus in chemistry. So what we can do is plot pressure versus 1 over temperature, and you get a straight line, and you can interpret it much better. And then it goes off on some calculations where you got to take the natural log or the analog in order to solve things, and it's really not practical. And the more I looked into it, it is required for AP, but I'm not going to include it here. Okay. All right. That was a sample exercise. So skip that. Skip all calculations. The last thing we're going to look at is changes of state. And we see that the graph, again, of temperature versus heat applied is called the heating curve. All right, I'm going to show you some of these things. The temperature a solid turns to a liquid is the melting point, which seems to be obvious. Now, what seems to be also obvious, which eludes most people, that temperature that the solid turns to a liquid is the melting point, is also the freezing point. So don't forget, the freezing point of water is 0 degrees Celsius, but that's also its melting point. So something goes on when we hit the melting point slash freezing point, or the boiling point slash condensation point, which we'll talk about in a second here. The energy required to accomplish this change is called the heat or enthalpy of fusion, which is delta H of fusion. Okay, so earlier we took a look at delta heat of vaporization is the point at which, or the energy that it takes to vaporize something, to put it in the gas phase, or the point where in which it'll condensate. Okay, so we have evaporation and condensation happening at this point, and now we see a different point where we have the delta heat of fusion, which is melting and freezing. Okay, so at this point we have two things going on, and if actually I'm probably going to get into this, but when I'm at either one of these 2 points, and I can stay at that substances, for example, water, if I'm at 0 degrees Celsius, I have freezing and I have melting going on at the exact same time. So let's take a look at some examples of that. Um, Actually, we'll take a look at this first. Okay. This is the heating curve. Now, you'll notice at this point here, all right, we see temperature increasing and heat being added this way. So I see some things going on. I notice that when a substance, such as water or ice, here it's a solid phase, as the temperature increases, the heat is being added, so heat is being transferred to the ice, and I notice that temperature increases. So temperature indeed goes up as the solid is gaining temperature, as it's gaining heat. Okay, now if I hit this point here, you'll notice temperature stays constant, because at this point in time, freezing and melting are happening at equal rates. Okay, if I were to stay at this temperature for water at 0 degrees Celsius, if I were to stay at this particular temperature, I would have an equilibrium of solid and liquid, okay, or freezing and melting, two opposing forces happening at equal rates, and they're dynamic. So I would have an equilibrium at this point in time. So I noticed that during a phase change, and this is important, during a phase change, there is no change in temperature even though heat continues to be added. Okay, so that's very important. Now, once I hit the point where the average temperature is above 0 degrees Celsius, I now have an increase in temperature while heat is being added. So now I'm at the liquid phase. So I notice that during a constant phase, solid increases in temperature as heat is being added. Liquid, temperature increases as heat is being added. I see an increase in both of those things. Okay, but now I'm here at the vaporization point, okay, or at the boiling point. And now again, I notice a flat line. So here is water's boiling point. And at the boiling point, if I were to stay at this point, I would have condensation and vaporization happening at a dynamic equilibrium. But I'm not. I'm going to increase that. And eventually you'll see that once all the average temperatures of all those particles is above 100 degrees Celsius, I'm now in the gas phase. Okay? You can see down here, if I'm at A, C, or E, I'm going to use the heat equation, which is the mass times the specific heat times the change in temperature. Okay, so that would be A, C, or E. And if I'm at B, which is a solid and liquid, I'm going to use this equation. And if I'm at E, I'm going to use this equation. Okay, with the only difference being the delta heat of fusion, the delta heat of vaporization, which either has to be given or you got to look that up. Okay? All right, so just be careful with that. I'm not going to go through any calculations on this, although it could pop up on the test, so just make sure you know how to do that. And if you have questions in the class as something to practice, I can tell you that. Okay, melting point discussion. Melting point is determined by the vapor pressure of the solid and the liquid. Again, the vapor pressure of the solid and liquid is strange because the melting point has to deal with the vapor pressure. So that must mean that if for something to melt, I must be having to deal with or try to understand or organize this idea of vapor pressure. Now, at the melting point, the vapor pressure of the liquid or the solid equals the vapor pressure of the liquid, which is strange to think that a solid could actually have a vapor pressure, but it's true. When I'm at melting point, those two pressures have to be the same. Two vapor pressures have to be equal. So let's take a look at this diagram here, okay? If I'm at a temperature which is above the melting point, if I'm above the melting point, that means there's going to be melting going on. So what happens here? Let's read this. It says vapor pressure in the solid must be higher than the liquid. So what happens is if the vapor pressure here, and again, it's above the melting point, so let's say I'm at 1 degree Celsius or so, the vapor pressure here is higher than the vapor pressure over here. Okay? So, therefore, the particles leave the solid and are entering the liquid phase. Okay? Now, this is just a contraption set up to see how this would all work. Okay? We don't see this contraption, this particular, this diagram going on in water, but it's a way for us to conceptualize what's actually going on. And actually, you can set this thing up and see this happen. So, therefore, if I'm above the melting point, the vapor pressure of the solid is greater than the pressure of that of the liquid. And so, therefore, water in the form of vapor will leave the solid phase and enter the liquid phase, and I see melting going on. Okay, so the liquid level rising, I see melting. Okay? Next, what if the temperature is below the freezing point? So let's say I'm at minus 1 degrees Celsius. And in here, I see the vapor pressure of the liquid being greater than the pressure of the solid. So now I see the particles in the liquid phase leaving the liquid phase, entering the solid phase, and I have freezing. Okay? This is all described in your book, but I think I do a little bit better job being more concise here. Your book goes on and on about this stuff. Okay? So that's what's going on there. Now, what if I'm exactly at the melting point, 0 degrees Celsius? Vapor pressure of the solid is equal to the vapor pressure of the liquid, and I have equal amounts this way, and dynamic equilibrium. Okay? So I wouldn't see either one of these things on either side increasing. Next, boiling point. Now, the boiling point is a point at which the vapor pressure equals the external pressure. So that means, see, we know that the boiling point of water is 100 degrees Celsius, but that's only 100 degrees Celsius when I am at sea level. So it has to deal with the pressure on from the external source. So we typically boil things in regular atmospheric pressure. Your house is open to the atmosphere, the outside, and so on. So you're boiling up some water for some macaroni, and you're trying to make this stuff, and it hits 100 degrees Celsius, and finally, check, you got boiling. But what if I was to get this stuff to be less than the boiling point? Then I could have water boil at a much lower temperature, which is what I showed you guys. All right, actually, I see that the time is increasing. What I'm going to do is stop right here and probably pick up on this and finish with one more video.